Thank you for the very nice introductory comments. I'm pleased to be speaking today to the Utah Academy of Sciences, Arts, and Letters at their annual meeting. It's an honor to give the keynote address today. The subject is from atomic bombs to nuclear energy. That's a rather broad subject, and I'll start first with atomic bombs. The first atomic bomb was detonated in New Mexico in 1945, and on the left shows a timeline of events leading up to this. In 1939, Einstein sent a letter to President Roosevelt noting the potentials of other countries developing atomic weapons. And in fact, that letter, I think, is on display yet at the New Mexico, at the Albuquerque, New Mexico Nuclear Museum. I saw it there, if I recall correctly, some years ago. Then in 1942, the Manhattan Project begins to develop nuclear weapons, and in 1945, at the Trinity test site at White Sands, New Mexico, the first atomic bomb was detonated. And we saw the famous, what's now the famous and well-known mushroom cloud form after this huge bomb explosion. Now, after the war, World War II, and the test at Trinity test site, a test at the White Sands test site in New Mexico, the U.S. moved its testing to the Nevada test site. And this is shown as a black dot on the slide, sort of the left. It's about 60 miles or so from Las Vegas. You can see on the map at the bottom is Las Vegas, and then there's Lake Mead, and you see upper right, you see St. George, Utah, and Hurricane, Utah, and Cedar City, Utah. And so the Nevada test site where the tests were conducted is located such that the prevailing winds from west to east would tend to blow radiation across southern Utah, and that did happen, and that's why sometimes the St. George, Hurricane, Cedar City even, are called the downwinders, downwind from the Nevada test site tests that were conducted. At the Nevada test site, there were above ground tests and there were underground tests. And the above ground tests shown on the left here, of course, is what they looked like at the time that were conducted. Many of these above ground tests were conducted, and of course did put radiation into the atmosphere, into the air. The below ground is sort of depicted by the slide on the right. Those craters, they're not bomb blasts. They're resulting from underground tests that were conducted, and after the test and a cavity was formed, then the Earth collapsed and creating these subsidence craters that are there. And so under each one of these was a underground nuclear test going. So that's what, on the right, what the Nevada test site looks like today. You can see these subsidence craters resulting from underground tests. Let me just comment a little more on the underground tests, because they were the complicated tests for sure. But underground testing is designed to contain the nuclear radiation underground, and it does very effectively. There are two types of tests conducted. One was called device test and one was effects test. Now, the device tests were simply to see if the bomb would go off and the energy created from the bomb. And all these craters on the right-hand side there, they're from device tests where they were testing the energy from the bomb and the reliability. The other test is the effects, nuclear effects tests, and they're much more complicated in some ways. The effects use the explosion to create the radiation to help understand the effects of this radiation on different components like electronics and shielding materials and so forth. And the bottom lower left on the slide, it kind of depicts the underground test showing the ball, the orange-brown ball there with the nuclear bomb in the middle, and it goes off. There's enough overburden, enough cover over it so that it doesn't create a crater. All the radiation stays underground. And then there's a long metal tube that maybe is a quarter mile long or longer. And the radiation from the bomb goes down this tube, and at the end of the tube is where you place your experiments in to be exposed to the nuclear radiation. The aperture at the bottom may be just a few inches in diameter, where at the other end, you can see in the upper right-hand picture from one of the underground tests that was made available to the public to see after the test. And you can see the big metal tank there that it was big enough to have an entire missile there that would be exposed to the radiation. So these nuclear effects tests were much more complicated, but doing them underground did keep all the radiation underground. Regarding the energy from a nuclear event, this is the famous and well-known Sedan crater at the Nevada test site. It's been open to the public. There are many tours, still tours today, going to look at. This was a nuclear bomb detonated in 1962. It was designed to be at what's called cratering depth, that is, at a depth so that it would indeed blast out all of the Earth. So this is a true crater created by the bomb blasting out the soil in this case. And the bomb had an energy for this one about 104,000 tons of TNT equivalent. So it was not a very big bomb as nuclear bombs go. Placed a little over 600 feet deep and created this crater, which is about over 1,200 feet in diameter at the surface and over 300 feet deep. Now, this is, to me, it's sort of mind-boggling that something like 12 million tons of soil was removed in several seconds. It's really mind-boggling to think that a bomb, and a fairly small one, created a hole in the earth like this. Now, the largest bomb ever connected, I believe Russia claims that they detonated the largest bomb, a hydrogen bomb. That was something of the order claimed to be 67 megatons, 67 million tons. Now, that would be something like 670 times bigger than the Sedan crater bomb here. To me, that's just sort of mind-boggling as to what would that be, 670 times larger? What would that look like? So that they claim that's the largest one. The U.S. detonated several, I believe, in the 1 megaton side, which is 10 times bigger than this. Well, here's the nuclear bombs story. It started with fission bombs, the atomic bomb, and moved to fusion bombs or the hydrogen bomb, much more powerful. Initially, they were designed to be dropped from an airplane, with the airplane could fly away to get out of the way of the bomb. Later, then they were designed to be delivered by intercontinental ballistic missiles. That is, a missile that would fly up out of the atmosphere, fly through destination, and re-enter the atmosphere, and then drop the bomb, if you will. The bombs range from the kiloton size, kilotons, 1,000 tons of TNT equivalent, from this kiloton size to many megaton size. From the 1945, the first test conducted at New Mexico, to 1963 is when the above-ground test ban treaty was put in place, and so no more above-ground tests were conducted by the U.S. after that. We had about over 1,000 U.S. bomb tests conducted in this interval, both above-ground and underground tests, and I moved on to 1990 when the Comprehensive Test Ban Treaty limited all nuclear testing. U.S., Russia agreed to that testing. The nuclear bombs moved to what was called mutually assured destruction. Interesting, isn't it, that each side realized that even though they could destroy their opponent, they would get destroyed too. Mutually assured destruction, which was a stabilizing phenomenon. It moved to exoatmospheric deterrence, where that if you set off a bomb in the outer atmosphere, above the atmosphere, that anything incoming, any incoming intercontinental ballistic missiles and decoys would all be destroyed as they were coming in. So that kind of deterrence was very effective. And I believe Russia violated the above-ground test ban treaty, maybe with U.S. concurrence, I don't know, in 1968, I believe, to demonstrate this exoatmospheric effect, how well it would work. We moved on to numbers limitations and then decommissioning of bombs, both US and Russia. US certainly has decommissioned a lot. I assume Russia has too. With after that, then reliability verification had to be done without tests. That is, after the Comprehensive Test Ban Treaty of 1990, since we can no longer do tests, we had to have reliability and verification assured without this testing periodically. That's kind of the story of the nuclear bombs up to today, if you will. Let me move now the rest of my talk to talk about nuclear energy. The first commercial, I think, electric generation nuclear reactor to put power in the grid, I think, was at the Westinghouse Electric Shippingport, Pennsylvania facility. This is a picture in 1958 when it was first went online in 1958, as I recall. I had the good fortune of seeing that when I was a young engineer. Westinghouse proudly took their new hires to this plant in July of 1958. That's what it looked like, and to see in this facility. That was a nuclear reactor right along the Ohio River. That's the Ohio River in the upper part of the picture, not far from Pittsburgh, Pennsylvania. It's sort of northwest, I guess, of Pittsburgh a little bit at Shippingport time. Well, when we think of nuclear power, often you see this big structures here. And I just want to note that those aren't really the important part of it in a way. I mean, they're cooling towers. These big things there, they're just the cooling tower. And what's coming out of them is not smoke, it's simply water vapor. So they're cooling tower, they're kind of harmless. They're needed for any large steam generating electricity plant, steam electricity generating plant. And they're cooling towers with steam coming out, they're not smoke at all. Here is a more critical part, maybe. One is on the left, shows a nuclear reactor with the lid taken off. That is, the reactor containment vessel has the top lid taken off, and you can see down into those squares, that's where you would slide your uranium fuel rods inside the reactor, and the radioactivity creates the heat then, which would heat maybe water or other substance. And it would not only cool the reactor, but then it would provide the heat energy to later produce electricity or use for other sources. That's on the left. Now, on the right, then, is the reactor control, reactor containment buildings. Those are the critical. So it's not this big tower that you often see that you look at, oh, it's for nuclear. No. It's this reactor on the left, and it's a containment vessel, which is cement, many feet thick cement bubbles that contain the reactors. Those are the critical parts. Let me just walk quickly through a nuclear electricity cycle, how it works. This is taken from the internet, so I just took a copy right off the internet. Looking at, but if you start on the upper left-hand side, which says mining, and first we have to mine uranium. And Utah became famous back in the 50s, I guess, due to uranium we found down around Moab and in that area. And so you mine the uranium, but then you enrich the ore. So through chemistry, it's called enriching it. The ore, but then the uranium you've enriched, the uranium you've concentrated, has mostly U-238, so it doesn't have the fissile U-235 that's desired for your reactors. So then you go to an enrichment facility where you enrich the uranium to increase the amount of U-235 in your uranium. And we're using low enriched uranium, 5% or so enriched uranium with 5% U-235. Then it goes to the fuel fabricating to make it into the rods or this configuration to go inside the reactor. Then it moves to the reactors. And of course, there's where it produces heat. And it goes to the steam generator, a conventional steam generator, if you will, to produce electricity, which goes into the grid. It's merged in with other sources of electric power through transmission lines and to distribution centers and onto your home. Now, there's one other loop there, that loop in the middle. The spent nuclear fuel from those reactors, once they're burned up, it goes on out. It's called services to remove them, and then they go somewhere for storage. Well, right now, they're stopping at this storage. In fact, they're not even leaving the facility. The storage is continuing in general at each of the nuclear reactor sites here in the US. And so it just stays there for decades, usually in a water pool, swimming pool, if you will. However, other countries, France, Sweden, for example, theirs goes in more of a circle. The spent fuel can go out, it goes to the used fuel treatment, and then it goes to a recycling or reprocessing plant. Our fuel was intended to go from the fuel treatment to permanent storage, like underground geologic permanent storage, but it doesn't. We've never been able to come up with agreement on this underground storage here in the US. So ours just stays on the road, but in other countries it goes to recycling and then can go back into the reactors to produce more heat, more electricity, it goes in a circle. And you end up with far less spent fuel that you do need to ultimately dispose of from site. So that's kind of the cycle. So from mining to concentration to enrichment of the uranium to fuel rods to reactors to steam electricity, which goes on to the grid and so forth. And then the spent fuel goes in a separate circle. Our spent fuel stops and stays right at the site, even though it was intended to ultimately go into underground storage. Well, the nuclear debate and public perceptions about nuclear are important and interesting. Nuclear debate today includes the nuclear energy, I say today, includes grid electricity and power for naval ships and submarines. That is, our naval ships and submarines, big aircraft carriers and submarines, are powered with nuclear reactors that create the energy for powering the ships and submarines. And we have, for nuclear electricity, nuclear energy, we use electricity. It produces only about 2% of world energy, but that's done in the form of about 10% of world electricity. And it's about 20% of US electricity. So nuclear today is providing about 20% of US electricity. We have about 40 plants with about 60 reactors providing that 20% of our electricity here in the US. So the public debate in the US tends to focus much on these about 40 electric plants regarding whether they should be closed or continue operation. And it focuses on the huge costs and the delays in new plants. There's, I think, 2 plants under construction in Georgia. They're about completed, but they've had huge cost overruns and huge delays in that construction for these plants. And to a lesser extent, debate is about spent fuel disposal. So that's a debate, is kind of whether we should keep the plants going or close them. And regarding the high costs and delays on new plants, and then debate about what to do with the spent fuel. Where do we go? Right now, as I mentioned, it's been kept at the 40 plants. Public perceptions include catastrophes such as Fukushima in Japan and Chernobyl and plants, and the 3 Mile Island danger here in the US. Those are all somewhat embedded in perceptions, public perceptions regarding radiation risks. Fukushima, Japan, you know what happened after the earthquake, and the plant Chernobyl in Ukraine, and the 3 Mile Island danger, it was contained, but very minimal radiation leak from 3 Mile Island. But nonetheless, these perceptions are created regarding radiation risk. For the general public, those spent fuel management issues are bigger in terms of the public perceptions and its impacts. It's the spent fuel, what to do with the spent fuel, and the strong not in my backyard perceptions here. To some, not in my backyard means not in my country. To some, not in my backyard means not in my state. And to many, it's an emotional issue. For utilities, their perceptions at the utilities, in my opinion, is quite different. It has to do with cost and schedule overruns. That is, if you look at the recent history of nuclear plant construction, the cost and schedule overruns were so huge. And when this is coupled with already negative feelings toward your nuclear, that really guides the utilities' perceptions. Regarding new designs and fuels, and there's much work going on. Weapons proliferation is of concern to a small group. The small group that still argues that world nuclear could lead to more nuclear weapons proliferation. Reactor designs and nuclear fuels, it's important. Let me say a few words about these. Nuclear reactors, that reactor, I showed you a picture before the reactor, what it looks like, and the nuclear fuel, that is how much it's rich, what is the nuclear fuel, and how it's allowed to radioactively decay, they go together. Reactor and the fuels go together in a very complex engineering atomic physics matter. And so it's not just that you have a reactor and then you have nuclear fuel, they're independent. No, far from it. Reactors and fuels very much go together. Now, many reactor designs and nuclear fuel options have been built and research tested. In fact, some say that all of the new reactor designs and fuel options that are even on the table being considered have already been built and research tested. So we know something about them. It seems unlikely, in my opinion, that the U.S. will see any additional conventional, what I call conventional, large-scale nuclear electricity power plants because of the high front-end costs and the long construction times. Costs and construction times are driven by extreme safety requirements, right or wrong. Nuclear safety requirements are indeed extreme. And permitting complexity, not just for nuclear, but overall permitting complexity, which in turn is driven much by public positions on different matters, particularly not in my backyard perceptions and feelings. New small scale and even micro scale reactors that could be fabricated primarily or totally in factories. And they might even be fueled in the factory. That is a small scale reactor, not the huge ones we usually think about, but a small reactor that might be 1 to 300 megawatts, could have most of the components fabricated in factories. And if you look at a micro reactor, a micro scale reactor might be the size of a shipping container almost. The large shipping containers are about 40 feet long. And so a micro reactor is that size, that could be literally built in the factory, even fueled in the factory, hauled on a truck to a site. And when it's out of fuel, you put it on the truck, haul it back to the factory, refuel it. So you would never refuel on site. So you have like small amounts of radioactive material in the site. And these reactors that are designed and built to be in what's called a fail-safe, that it cannot fail mode, cannot fail no matter what you do to them. You can blast them, you can destroy them, you can turn off power, they can go through earthquakes. They simply shut themselves down under those conditions. These small-scale modular reactors, they're called, and the micro reactors, to me, offer great opportunities. But to accomplish, expanded nuclear energy, public perceptions must change. With unreasonable permitting delays and not in my backyard position, simply cannot be allowed to an unreasonable extent. And that's complicated, very complicated matter. Just a comment on these small scale reactors, because I really think the small scale reactors are a thing of the future, and the modular reactors too. There's 2 private companies working on them, maybe more, but 2 that are often in the news. TerraPower, with some interactions with GE Hitachi, backed by Bill Gates, I think TerraPower is. They're going forward with a small-scale modular reactor in Kimmer, Wyoming. It's a Kimmer, Wyoming plant for Pacific Corp. It's a 345 megawatt plant. It's a fail-safe design that cannot fail design. Does require higher enriched nuclear fuel, and that's a problem right now because the U.S. does not have any enrichment plants operating at the moment, as I understand. We've been actually buying our enriched fuel, unbelievable as it may sound, we've been buying it from Russia. And we also get some as we decommission more and more nuclear bombs, and we are decommissioning some nuclear bombs, and so then we get some enriched fuel from them, and the rest I think we've been buying as we need from Russia. These reactors will produce much smaller spent fuel streams if they can use the higher enriched nuclear fuel. So this TerraPower plant is in Kimmer. It was scheduled to open in a couple of years, but they just announced a month or two ago a delay because of this matter of not being able to get the enriched nuclear fuel. You can't count on it coming from Russia, I guess, at the moment. So anyway, that's the problem with that Kimmer, Wyoming plant, but it is furthest along as I understand. The other company is NuScale Power. They have pictures of a 77 megawatt, they would call it a micro scale, I think, reactor. And that's a picture of it on the left that came from NuScale. They don't show much in terms of detail of what's inside, but that's a picture just taken from their website. But that picture shows something that's about 9 feet diameter, about 50 feet long, fail-safe design, allegedly. Also requires higher enriched fuel, just like the TerraPower unit going into Kimmer, Wyoming, and will produce small spent fuel streams. So anyway, that's what a micro reactor could look like on the left side of the picture. 9 feet in diameter. You can haul that in a truck quite easily, and 50 feet long. It could be removed, taken back to the factory for refueling as needed. So let me conclude by commenting on the nuclear energy story. Nuclear energy from 1958, the Westinghouse shipping boat reactor, to about 60 reactors we have today, now producing about 20% of U.S. 20% of U.S. electricity. It's a mature industry. The 1950s near-free nuclear electricity vision, that's what it was. I recall the 1950s. Nuclear energy was projected to possibly be so cheap that you wouldn't even have a meter on your house. It'd be like your phone. You just pay a small monthly fee, use all you want, almost free. That vision today requires large upfront costs, huge upfront costs, and long construction time for these big power plants, with lingering spent fuel issues. Yet, what do we do with the spent fuel in these? Uranium ore comes from Canada. We don't, to my knowledge, I don't think we're mining any uranium in the U.S. We buy it from Canada. Saskatchewan has a lot of uranium, maybe Ontario too. We get enriched fuel from decommissioned nuclear weapons and purchase enriched fuel from Russia, which probably is ending now, maybe, I'm not sure. Permanent nuclear spent fuel storage seems as far away as ever, primarily continuing a political problem, not a technical problem. That is, the defense waste is stored underground. The waste pilot project, WIP waste project, is in Carlsbad, New Mexico, near Carlsbad, New Mexico. It's been storing defense spent fuel for decades, fine. So really, this is primarily a political problem, not in my backyard, not a technical problem as to where we store the waste fuel. Radiation concerns have caused extreme safety requirements, right or wrong, really extreme. In my opinion, they're not based on medical criteria at all. They're simply based on what you can measure. If you can measure it, it's too much. And great permitting complications. Indeed, there's talk about permitting of all sorts of things, electric utility lines, pipelines, and more, with changes highly, highly difficult. I don't have a quick answer to that. The permitting is a complex issue, very difficult as to what's fair and what do we want to do with regard to permitting. Small modular reactors, the SMRs, and micro nuclear reactors, along with the higher enriched fuels, could allow nuclear energy expansion. But I think it will take that to really see substantial nuclear energy expansion, whether in the US or even worldwide. And this could provide more electricity. It could provide a source for making hydrogen, nuclear produced hydrogen, not a new idea. US had a nuclear hydrogen program, which was paused or canceled about 2016, I think. Nuclear desalination of water. Water is a major issue, particularly for us here in the West. The desalination of water. The U.S. right now injects over 50 million barrels of salt water every day from the oil industry. 50 million barrels. Maybe some of that could be desalination with a nuclear reactor. And nuclear could provide other direct heat applications. So nuclear could do more than just providing electricity. And I think it has to if it's going to help with the energy transition. My conclusions, from atomic bombs to nuclear energy, over 8 decades, 80 years, has happened in my lifetime. I've seen it. With continual issues. I mean, continually there was issues. There was issues on the bomb. Should we drop the bomb or not? Should we have dropped the bomb? Should we develop nuclear weapons? There's been continual debate about the nuclear plants where they could be sited with. So in 80 years that I've seen, there's been continual issues with nuclear. Nuclear weapons will be continued as part of the U.S. defense. Look, the genie is out of the bottle. It's not going to change. Whether we could destroy all our weapons, but the rest of the world is not going to. You cannot count on your adversary to necessarily destroy their weapons. So nuclear weapons are going to be continued. In fact, we have new players in North Korea and Iran, for example, now. Nuclear energy must be part of the energy transition, in my opinion, away from fossil fuels. If there is to be an energy transition away from at least reducing the amount of energy from fossil fuels, it has to include nuclear. Nuclear now only provides about 2% of world energy, but about 20% of our electricity here in the US. If we're to continue reducing our dependence, say, in the US on fossil fuels a little bit, or at least preventing its growth, nuclear has to be a strong player. I'd like to acknowledge in closing that I've been a strong advocate of nuclear energy for quite a while, but some time ago I realized I really didn't know much about it. And so I decided to look into this, to work on it. And I put together a very fine team of very good people, very smart people. Professor Glenn Zorden is at the University of Utah. He's head of the nuclear program there. He's very well known. He's certainly very much an expert on nuclear. Stephen O'Meara from Idaho National Laboratory. Stephen O'Meara is very well known also, and very nice person, great to work with. Idaho National Laboratory, right next door to us, is probably the world's leader on nuclear reactors. Kim McCarter retired from the University of Utah from mining. Kim looked into the uranium part. Do we have enough uranium in the world to increase it? Jen Green she's an environmental consultant, but she did the public perceptions, which was interesting, really interesting, surprising. She found how few people even knew what Fukushima was, or Chernobyl. They kind of heard of something in Japan, but when you mention what's Fukushima, a lot of people, even though they had strong opinions, either for or against nuclear, they said, what's Fukushima? Professor John McLennan from the University of Utah, now, he looked into the reactor materials, because that's critical, particularly if you want to use nuclear for other than electricity, where you want direct heat applications like production of hydrogen, for example. Reactor materials are very important, John. So anyway, with that team, we put together an overview. It's a rather long overview, but it's called Potential and Challenges of Expanded Nuclear Energy. It's available if you want to read more about it. It's written for the layperson. It's not a nuclear physics or a lot of equations. It's for the layperson. You can find it at that website there. We just put it on there as a placeholder. Just go to the news, and you can click on your phone or your computer and quickly read it or download it as you like. With that, I again extend my appreciation for being invited to give this keynote address at the Utah Academy of Sciences, Arts, and Letters. And I wish all the best.